Yes, and Tevin is also giving some contribution there, physical point in a rasa image. Thank you so much. I think you are still a very up to date with under the understanding of the concept of the pixel. And as we are told by Moiri, pixel is a picture element, or the word itself comes from the words picture element. So that's that helps us to get to that point. That pixel is a word that is made from the two words. So picture and element, as Moiri has stated there. So from the two words, you get a pixel by just picking the P-I, and of course the sound of C and T to get the pix. And then from the word element, you get the EL to make the word pixel. So it's actually coming from that direct creation of the word picture element. Okay, so I think we can go on now. Thank you for the contributions. Okay, so again, I'm resharing the document, and this time I think the system is doing good, so we should have it displaying in a short while. Okay, well, yes, there we are. So we can continue now. And it says, so we have some picking from where we reached, is that the document continues that bitmaps are an image format suited for creation of. So when we want to have these types of characteristics or quality, then we go for bitmaps. So when we want to create a photorealistic images, when you want to create complex drawings, when you want to develop images that require fine detail. In other words, images that are showing almost every detail, then we go for bitmaps. And of course, this is in comparison, of course, with vector graphics. All right, bitmap images are known as paint graphics, and bitmap images can have varying bit and color depths. So those are important words in the concept of computer graphics that we need to consider bit and color depths. So when it comes to thinking about, of course, the last statement says more bits provide more color depth. So again, I would like to believe that you are familiar with this particular concept of bit depth and bit color depths. So this when we're thinking about the colors, how does the computer show the colors, and what is the capacity of the computer showing or being able to display the colors? How many can it do? And that is what this concept is trying to bring up. That this representation that we are saying, because of course it's what we call the rendering is of course coming from computer coding. So again, just like other data in the computer is represented by codes. So even here we have to use codes to represent different things, to represent the image itself, and also the color that the image may have. So all that is an issue of coding using the bits. So that's what we're talking about, the bits. The bits are the ones which are used for coding information or data generally, whether it is images, whether it is sound, of course, they're coming from the computer, whether it is just the general outline of something, that will all require the concept of bits. So what is a bit depth and what is color depth? But as he said here, notice that he says that the more the bits, the more the color depth. In other words, those two words are also associated with each other. So the bits is the number of bits. The bit depth is the number of bits that you are going to the system uses to represent the colors, or essentially the pixel. So how many bits do you want to use per pixel? Now remember, pixel is a point or is a dot, is what we are calling a picture element, but in a practical understanding, we can say it's a dot. It is a point. Of course, the word point is closer than the dot because the dot seems to be physical, but a point does not have to be physical. Although if you are to show a point, of course, again, you need to do it physically, probably by using a color. So if you think in terms of the points, then we have the pixel. So the pixel is a point, but now we are asking in terms of the coding, that point. So how many bits do you want to use to code that particular point? And that is what we call the bit depth. Now, there is that issue of how many bits would the system use? Of course, it's not you who suggests, it's the system that you are using. So whoever built the system, in this case, of course, the computer, if it's a computer, how many bits does that computer use for coding the colors? If it is the camera, because of course you can take you can take a photo, and of course this is also based on of course this is in this case we are talking about the digital camera, not the old technology of the cameras, but the digital camera. When it takes a photo, what is the technology there in the camera? So how many bits does it use to create the image when the photo is taken? So how many bits does each, or do we use to code a point, an image point, what we are calling a pixel? So that's this particular slide here is trying to describe that concept. And originally, the computers could only show two colors, just black or white, so black or white. Now, if your system is meant to show only two colors, and in this case, of course, it can be any other color, as long as there are two colors, then you need only to use one bit. You need only one bit to code your point. You can you need only one bit. You see, remember the bits are, in terms of human expression of the bits, is either a 0 or a 1. So all you need to decide is if you want if the system that is being built is only to display only 2 colors, then you just need to use 1 bit to do that. So that 1 bit, either the 0 or the 1, represents one of the color, and the other bit represents the other color. So if it's a black and white, so the parts that you want to be black, maybe normally 0 is used for the parts that are black. So the parts that are black will be all zeros, and the parts that are white, of course, then we code them with bit 1. So you only need 2 bits to do that. So 1 bit at a time, of course. So okay, one bit to color your point. So the parts that are the point is represented by a 0 will be black, and the points where they are represented with a 1 will be white. So then you can have a black and white kind of an image. So you need so the number, but you see, so this table, as I have said, is trying to show that progression. So if you need only two colors, then you just need 1 bit per point. But then so the number of bits determine the number of colors that you can do. So if you use 1 bit, you can only do 2 colors. If you want to represent your points with the 2 bits per point, then you can have a total of 4 colors possible to represent whatever you are representing as an image. So that image, you should be able to show 4 colors. If you use 4 bits, then you can have a total of 16 colors that your computer can display. So 16 colors, and of course, this part here is showing us the number of bit combinations in the point. So 1 bit per point, then 1 color can be 0, 1 color can be 1. 2 bits, 1 color can be represented by bits 0, 0. The other one can be coded 0, 1. The other one can be coded 1, 0. And the other one can be coded 1, 1. So of course, these are the codes that represent the color. So in the 2-bit case, maybe 0, 0 might be maybe black. 0, 1 is coding maybe white. 1, 0 may be coding maybe a red, and 1, 1 could be coding maybe yellow. So it's a matter of the code. Which code gives you a certain color? Which code gives you a black? Which code gives you a white? Which code gives you a red? Which code gives you a yellow, etc. And that the number of colors that you can code will be dependent on the number of bits that you are using to do these representations, to code your colors. So if you are using 4 bits to code your color, then you can have all the various bit combinations that you have available, and therefore you can also have as many colors as different coding patterns that you can have with the bits. So in this case, it is 16. Now, of course, you can notice a pattern there that the number of colors is 2 to the power the number of bits that you are using for your coding per color. So if you're using 1 bit, then the total number of colors you can have is 2 to the power 1. So they are all powers of 2. If you have 2 bits, it is 4 to the power 2. Of course, it should be 2 to the power 2 colors, possible colors. If you are using 4 bits, then you can have 2 to the power 4 different colors possible. And so it will be, so 2 to the power 4 is 16. And that pattern, of course, continues on. And of course, that also is a kind of the pattern that the technology has had. But now we are using very many bits, of course, not many in terms of that number, but it's, compared with the past, we are using many bits to color or to represent or to code code the colors that and those codes represents the number of colors that your computer is able to produce. Okay, so there is what we used to call monochrome. So when the computer can show only two colors, we used to call it monochrome. But otherwise, with the time, of course, the technology has improved, and the computers now can show very many colors. And of course, remember, even the number of colors that you can show also depend on the processor. So if the processor is not very powerful, or in this case, of course, the graphics processor is not very powerful. Of course, both the graphics processor as well as the main processor, if they are not powerful, of course, even if they could have maybe this system, of course, they may, the manufacturers cannot try to force the computer to do what it may not be able to do. But otherwise, you might find this difference, the difference between how your image shows in a certain computer, depending on the capability, the color capability of your computer or your phone. In this case, you can see differences in the way the colors are displayed. You find that sometimes you take your image in one computer or in one phone, and it shows some colors in a certain way, but you take it to another computer or phone, and you find that the images are not looking similar in terms of the color, and that is because of the capacity of or the capability of the processing power of that computer or the phone. So it's very important. So although we may be talking of maybe an image that was made using maybe a certain level of bits, but sometimes you may still miss some colors when you display that particular image with some other system, because the way the colors will be displayed will also be a factor of the type of the power of that particular device. But anyway, in terms of creating colors, programming the colors, so the bits, the number of bits will determine the highest number of colors that that computer can actually display. And so with 8 bits, so again, it is 2 to the power 8, and in that case, that system would be capable of showing 256 different colors. And so we continue on up to where we are now. We are at that 2. Just in case, so the next slide here should be showing okay, 24. Sorry, I think I went too fast. So we have 24. So we also, 24 is also very powerful. This one you can show very many colors, as it says here, in the millions. That system is capable of showing colors in the millions, and creating, actually, not only does it create, not only does it display the colors, but of course, when it comes to creating the colors and displaying them, so it is capable of creating millions of colors, or it is showing or displaying millions of colors. So it all depends on the circumstances, and in the environment, we have very many colors. So when we look around and we see our environment, the trees and all the plants, we have very many colors. When you talk about green, you end up then talking about the shades of green, and you find that by the time you finish up with the shades, we actually have very many colors. So the system with using 24 bits. So the number of bits that you use per point, that is what we call the bit depth. The bit depth is the number of bits that you are using to code a point of color. And of course, the total number of colors that can come from that coding then is what we are calling the color depth. The color depth. So that's the explanations of the two words, the bit depth and color depth. Although sometimes when you are reading various sources, sometimes these words are mixed up, but originally, and the common usage of those words is that bit depth is the number of bits that you are using to code a point, a single point, and the color depth is the total number of colors that coding is capable of displaying. Okay, so then we have that 2 bits according to this document, and I think it's very easy to do this calculation, because if you're using that 2 bits to code a point, if you're using that 2 bits to code a point, then it means you would be doing 2 to the power 32. 2 to the power 32 will reach the trillion. Okay, so if you're using that 2 bits to do your coding, then it could reach to the trillion. Now, for the sake of demonstration, I think we can try to do a simple demonstration at the whiteboard. So let me remove the screen share for a short moment. Just we interact at the whiteboard, and we try to revisit this concept of the bits. So just a short demonstration. I'll try to see if I can be able to do some drawing there on the whiteboard. So let me remove the screen share. We go to the whiteboard, and I try to do some drawing there to demonstrate something small about color, the concept of the bits for coding the colors. Okay, so we are there. And so when it comes to the concept of what we are calling the bit depth, so how does it work? So just trying to do a demonstration. It's because this system is not very easy to use all the time. Some things that are not very easy to do with the whiteboard, but nonetheless, we can still use it to do some demonstration. So if you are, suppose, let me do the simplest that is possible, so that we don't use too much time, is suppose we assume that we are using an 8-bit system for coding. So that will be the bit depth. Sorry, I think I made let me make it bigger, my space for the text. Let me make it bigger. So we're saying let the bit depth to be, let it be 8, the 8 bits. So what I want to demonstrate is how are these bits used to represent your colors. So now again, there is towards the end we'll also be talking about the various models of developing these colors. We have models, and the main one, the most popular model is what we call it the RGB model. So let's assume that we're going to use the RGB model here. So use RGB model. Of course, this represents colors, RGB, so red, green, and blue. So of course, these are a way of now these are taken as the primary colors when it comes to graphics. Primary colors which you can mix up and create the other colors. So now this is familiar even from some of our past lessons about the primary colors and secondary colors. And so we might ask ourselves, so what are all these colors and how can we make them? So it's just a matter of mixing these, and of course, this is a model. It really doesn't mean that there is a kind of a mixing that you do. It's just a coding. And by coding that, of course, it's able to vary the type of colors that the system can display. And so so if you use a RGB model, sorry, I should have written the word there. But again, these words will come to talk about the models later. But for the sake of this demonstration, let's adopt a model. So if you use the RGB model, sorry, I think I made my text too big there. Let me reduce it so it can show. Okay, so then now with this one, with the bit depth of 8 bits, okay. Right, I think there is something that I need to, what I want to use a pencil here, not the line. Now what I want is to write, so with the 8 bits as your color depth, then you can make 256 colors. I think I already said that, but let's keep put it there as well. So you can make 256 different colors. So according to the to what we have said, so if you have 8 bits, then you can make 2 to the power 8 different colors, or the system will be able to display 256 different colors. So, but notice that you have now to adopt a certain model. And so if, of course, I'm picking this because it's simpler to talk about this from our experience of the colors are red, blue, green, and blue. So what we do is like the way people, mix up, paints, of course. But of course, in this case, it's not paint. In this case, what we are mixing, we can say we are mixing colors. So we mix colors. But we'll come to look at that a little more later. So how do we therefore get the other colors? And we say that it's just a matter of mixing up your various colors. So what you do now, if it's 8 bits, you actually distribute them amongst your 3 colors here. So each of these, the total, the RGB, the total will be 8 bits because it's going to be representing a point again. So it's going to be representing a point that can be used now to create your diagram or whatever is being represented. Remember, these diagrams could be drawn, but they could also be coming from other sources. For example, if you took a photo, there is a way of displaying your photo at the computer, certainly. And of course, at the mobile phone, if it's a digital, it has the camera, and you can take a photo, then you can then display the photo. So we're saying, how do we make that image? And then we display it. So it's a matter of coding. It is coded, and the coding, of course, we also take the issue of the color. So if you are you had let's say it's a photo, and you had your clothing had colors, several colors, different colors here and there. So how do we capture that color? Then it is displayed. So we have the computers adopt a model like this one. And if you are using 8 bits, then the 8 bits will be distributed among the three, let me call them the 3 components of making the color that is going to show. And so there will be the number of bits that will be, normally the way it goes is that 2, 3, they will be distributed into 3, 3, 2. So red will be having 3 bits, G will be 3 bits, and then B will be 2 bits. And then now those bits, remember they are zeros and ones. So if they are 3 bits, so for example, for the red, red, if it is using 3 bits, how many different combinations can you make out of 3 bits? And I'm sure you can easily do that. I think that would be a good point of interaction. So how many different combinations of codes can you make out of 3 bits? Let me see a number of you responding to that. So how many different kinds of codes? Different unique codes. I'm sure you must have done some interaction with that in the past. So how many? Yes, some of you are giving in bits there. So Ezra is giving one of the combination. Yes, the combination. So I want the combination. Yes, that's also good. But you can also tell me how many different combinations are those. Yes, several of you are trying to give the combinations. Yes, those are what will finally give you the total number. The total number of combinations you can make out of 3 bits. Yes, so 0, all 1, then 0, 1, 0. And I'm reading from Pelu. 001 and the 100. Of course, they continue. Yes, so that's good, but we need some more. Yes, Ezra had put the first one 00, and then said etc. Yes, it's all right. Of course, sometimes we want to do this as a teamwork. We can see more. So I think nobody has put all of them yet. So Ian Kimathi, Tieno Brand have also put some representation, but you still haven't reached the total numbers. There are still some more combinations that we can make. Yes, but that's good. So you can notice that there are many combinations, of course. So let me see. Ian Kimathi has put that. I think you added some more. Then Ian has added, okay, that's Ian again, has added 101, which was not in the previous list. Yes, and I think with that we have the total. So actually, that should be the total. number of combinations. There should be 8. So I don't know what Mamboreo has put. Is that a total of 8? Yeah, it looks like 8. Yes, and you'll notice, of course, it's just as like we are doing when we are saying how many colors can the combination make. It is the same concept. It is just 2 to the power 3. So if you have 3 bits, the number of different combinations that you can make will be 2 to the power 3. 2 to the power the number of bits that you are using for your coding. Yes, so thank you for that participation. And so we're saying that if you give 3 bits to red, so red alone can participate in 8 different ways. Of course, this is the same mathematics that was being done sometime. The mathematics of, was it, we talked about permutations and combinations. So we talk about that, but I don't want to go back to the mathematics. But if you can recall that, those mathematics could also may help you to deal with that question. But anyway, in a simpler way, is that if you have 3 bits that you're using to do your coding, so the red part, now again, we may ask ourselves, so why should we have so many colors representing the red? Of course, again, I take you back to the concept of colors. Colors are what we call the shade. So you can say this is red, but this is a shade of red. And of course, in this case, some of the colors that the computer may come up with may not necessarily be called really a shade of red. It may actually deviate completely from red, and it now looks something completely different. But that is the same concept here, where you can have the red that is maybe you can say is a deep red, a light red, etc. The shades of red. So those are what we'll be making by doing the combinations that we are doing here. We are trying to organize, and which we have been helped by Emmanuel to come up with the list here. And I guess also Mamboleo seemed to also have captured all the combinations. Did Emmanuel have all the 8? Yes, they are 8. Yes, thank you. Also, you are also confirming Emmanuel there. But I'm checking and I'm missing one. I can't see 101 in your list. So did you repeat something? Yes, you repeated 001. Because your combination there is 8, but I'm noticing I can't see 101. Which means you must have repeated one of your combinations. But anyway, so we may be asking ourselves, so how? So if we give 3 of the bits to R, so what? How does that help? And so yeah, I'm trying to explain from the analogy of the usual colors that we have is that even with the usual colors we use, we talk of different reds, a deep red, and that something else. And of course, as it makes maybe it becomes a lighter and a lighter, probably it now starts turning to some other colors. And that is exactly what will be happening when we are doing the mixing here. So give R 3 bits, give G 3 bits, and give B the remaining 2 bits. And with the part, so now you can look at them as a parts. So the part of red can keep changing with all those 8 combinations. So at some point it is 00. At another point it is 001. Depending on the color that the computer want to make, they need to keep on changing the number, the way the bit combinations are done for R. And that the same thing will happen for G. Okay, for the G, again the same concept. So of course they also breathe, so it is a similar combination with that of the R. And then for the B, we are having only two. So again, of course, the similar way of developing how many different ways that how many different unique codes will be coming at the B part. But now the mix of all of them, of course, make up a certain code. So for example, suppose we choose 000. Now you can even choose all zeros. Now that would be a combination one color, because of course it is not now red, green, and blue, but it is a combination of your bits that make now a certain color. So maybe when we combine red and the green and the blue, maybe it is white. I don't know. I don't know if it's all zeros. It actually means no color. And so if everything is zero, usually it will be representing black. And then if they are all 111, because there is that code where all of them can be all ones, then in that case, that is likely to be representing the white color. So the white color. And then the other combinations then create different other colors, the red, the green, the blue, and all the other colors up to a total of 256, because as we said, with 8 bits for the point. Now remember, the 8 bits is for the point, but they are also developed in 3 components. So it's like there are 3 components that make up your point, or the color that point has. The color that point has is represented as 3 components that get mixed up in different ways, and then they give us now the color, the resulting color. So maybe when we mix, when don't have, when everything is zero, maybe we end up having the black. If we have all of them are ones, then it becomes the white. And then of course, if it's any of the other combinations, then they keep on giving different colors. The yellow, so the yellow, sorry. So the yellow, maybe the orange, the and you have all these colors. If you look at your computer, you see it. It talks of so many colors. Sometimes they are even written in words, but others you can only see them as just a color, like the color wheel. There's somewhere in your computer that can show what is called the color wheel, whether it is in one of the documents that use color, is Microsoft Word or is a PowerPoint, where it picks the colors. There is either a color wheel or what is also called a color palette or a color box, where you can pick colors. So all those shades of colors, then they are made in that way. And when it comes to the total number of colors that you can have, then it is 2 to the power the number of bits that you are using to create or to develop the way the coding is done by your computer. So if you are using 8 bits, then you can have a total of 256 different colors that your computer is capable of displaying. Now, I think that is sufficient in terms of demonstrating that. Unless there is a question, maybe let me allow just a short moment of interaction again before we continue. So will allow us a short time of asking a point of clarification, or a question of a different kind, but maybe related to what we are looking at, images in multimedia. So thank you. Manuel, yes, you did. You made the correction for your codes. Yes, and so you can notice that it was one that was missing. Yes, Godfrey, thank you also for reminding me. Sorry, these notes are still, I think this particular document is not showing yet at the portal. Sorry, because of the many things that we are trying to catch up with, so that these, our studies can continue in this time of, sorry, I'm getting a bit hoarse. Let me clear my throat with some water. All right. So I was saying the notes, I'll put them in a short while. So the notes will show this document we are using for looking at the images. Yes. Then there is Wanjara also is reminding us. Yes, that's very correct. Pixel is the same as, so when we say point, sometimes also say dot, we are also talking about the same thing, pixel. Of course, the correct technical name is pixel, but sometimes we also call it, for this purpose of just trying to do an analogy, we also call them points, we call them dots sometimes, but there is no dot, there is no physical point. So pixel should be the best word here. So, okay, that's correct, Ian. Sorry, I think I was getting a bit hoarse here. Yes, Ian is also confirming about the colors. Yes, that's good. About the zero and the white being represented. But you're asking also a question there, is it right to say that the two mix to produce the RGB, and the RGB then forms a broader palette of colors? Yes, that's a question. And Mabaleo is saying something there. Is yes, Mabaleo, are you responding to Ian's question? Mabaleo, you can confirm that so I don't take that you have written some explanation there, Mamboleo. Are you giving a response to Ian's question? Yes, yes, Mamboleo is responding to Ian, and maybe you can have more contributions as it relates to Ian's comment, and actually it's a question. Somebody else, let's see more contributions. If you would like also to add, how would you respond to that? It's a question that Ian is asking. How would you respond to that? Some more people, let's say at least maybe some 3 more people. How would you respond to that? Yes, some more contributions to that. So Ian is saying if 0 is black and 1 is white, so is it right to say that the two mix to produce the RGB? And the RGB then forms a broader palette of colors. So Maboleo is responding that it is that way. He's agreeing with he's turning the, of course, the Ian's question to the answer as well. Nonetheless, I think there is something that may not be. I would think that may not be the case, because when you say 0 is black and 1 is white. Now notice that you're already adopting a coding. Okay, you are adopting a coding, which of course is not the case with today's computers. Of course, they are no longer using that coding. You see, you are already doing a coding there and saying, let 0 represent black and let 1 represent white. So already you have your colors. So they cannot build the RGB, all right? Because already you have already put a coding. You have already decided on a coding system. But you notice that your coding system is only for 2 colors. Unless, of course, you are saying that any place where there is a 0 is black. But don't forget, this is just a code. So the code depends on what you decide. Of course, in this case, computer engineers are the ones who are going to decide the coding system that they are going to use. Will they use a 1 bit for to represent the point? And of course, the point is what makes the whatever you are seeing. So whatever you see is a combination of many points, and then the way that those points will be spread. The way those points will be spread, each point has a color. Each point adopts a color according to the coding. So the way the points will be spread around the part that it makes your image, then those colors will show in that pattern, the pattern of your points. Let me, although it may not be very easy to do that this time, but let me attempt to just try to capture the concept of the points and how they finally become the colors, that we should see. So this time I need to pick let me see, we can use what? Let's use the black to do our what I want to do is to use the ellipse or circle to represent my points. Remember, they are very small. They are very, very small. So this point, this now I may not draw it very well. Of course, they should be in a straight line, but it may be a bit challenging for me to put them in a straight line. But essentially, the points that makes your image are normally arranged like in a rectangular format. They are rectangular. So each of these points has a color depending on the coding system that is being used. So if it's a coding system of 1 bit per point, so look, we are looking at these circles that I'm drawing here as very small circles as our points, whatever we are calling the pixels. But remember, the pixels are very small. It's a very, very small. It takes a very small space, so to speak, at your computer system. Of course, at the graphics system, it should take a very small space, and of course, in the memory as well, because of course, the representation of what you are making, of course, will be represented in memory. It will be stored in memory. These bits will be in memory, or the bits that you are talking about that make up. So this, I'm trying to organize them into a rectangle. Okay, they will be like in a rectangle like this. And of course, mine is they should be a little more symmetrical. They should be in straight lines, horizontally and vertically. But what we are saying is that, so each of these points here, each of these circles represent the point, what we are calling the pixel, and each of them will have a color. So the color that it will show, then depending on the dominance of that color, so how many so suppose we want to show red. First of all, that is going to be dependent on the coding, what we are calling the bit depth. So how many bits represent a point or a pixel, you know? So the coding a pixel. When you want to code a pixel, how many bits does your system use? Does it use 1 bit per pixel? Does it use 2 bits per pixel? Does it use 16 bits per pixel? So if your system is using 8 bits for our demonstration here, then each of these points here, which these of course these are circles, but we are taking as a point. So each of these points is represented by 8 bits. 8 bits, all of them. Each of them is 8 bits. The difference is the combination. The difference is the combination of the ones, the zeros and the ones. So the first one at the top left is 1 pixel, but it is coded with 8 bits. And those 8 bits could be all zeros. Could be all zeros. So we come to the next at the top line of my points. The next one, the second point at the top is also 8 bits, but it's because remember that once you choose the coding, that will be used by all the points. So if you use 8 bits, because it is for the purpose of coding your pixels, So, but each will therefore be 888. So the first one will be 8, the next one will be 8, the next one will be 8, the next one will be 8. But now, if they are not the same color, it means that they are using different combinations of the bits, the 8 bits. So if they are all zeros, each of them is represented by 000. So if the first one is 8 zeros, the second one on the top 8 zeros, the next one at the top 8 zeros, the next one at the top 8 zeros, and that continues for all these points, then the color we see will be black. So this space here, this rectangular part of space that will be shown at your screen, it will be black, or it's an image that you are drawing, and all the pixels are 80 zeros, 80 zeros, 80 zeros. Then it means that all of them, each of these points, each of these pixels is black, black, black. And of course, the total color for that whole space that they are covering, therefore, that space will be black. But that black is actually made up by small dots of black. In other words, it's not a continuous black like the way you paint. Instead, it is only showing black, but it's because the points are so close to each other, and each is black. So each is black. So that space there, that rectangular space there, will be looking black. Now, but what about if we want to see other colors? So again, depending on the code, for example, the code for red. So if all these points they have the code for red, and so each of them is red, then that space, the whole of that space will be looking red. And of course, we do have sometimes, of course, it's a mix. Not everything is we don't have just one color for the whole space. Maybe one of the Some of these are black. They could be black. Some of them are, they could be maybe yellow. Maybe here we may be having 3 colors. So that again will depend on the color of the points. So probably, maybe sometimes we could have so let me just try to also do a demonstration there. So if I just use the rectangle to display that, maybe suppose these 4 have the color of yellow. That's possible. Then that part will be looking yellow. This part maybe these others, these 4 again, maybe they are, each of them has a color of red. Then the whole of that space will be red. And this one, so suppose we choose another color for these other 4 points again. These 4 points, maybe they have a color of orange. Then that part will be orange. And maybe for the sake of just demonstration, let's say that this one has a different color, another color. Then that part will be looking that color. So for the sake of just trying to do that in a more complete way, let's write the color for each of these rectangular spaces. We are saying that each of these rectangular spaces are using a code for a certain color. So let's just assume, of course, for the sake of time, this part, the ones which are here, this corner, they are all red. So that space will be red because the points are red, all of them. And this one, so if the colors, all of these are, let's say they are green, then the whole of that space will become green. So if the pixels have the code of green, so each pixel is green, then that part, the whole of that part, because of the pixels, will be green. The same with the others, of course. Let me just, sorry, I needed to select the one for the text here. So this part, we are saying it, the pixels here have the color, maybe, let's say green. Because we already have the green. So maybe this one is orange. So we want to have different colors. Then the whole of this part here, because of the pixels, and the pixel is because of the code. So each of these, we are assuming that each of these circles here, which we are representing the points, the pixel, we are saying each of them is coded orange. If each of them is coded orange, then the whole of this space will be orange. So the other one, for the sake of completing that process, we can also have this one also assume a certain color. Let's say this one is purple. So if each of the pixel of that one is did not come out very well, so let me put it lower here. That this part here has a purple. Okay, so that's what we're saying. Depending on the code of your point, and of course, first of all, it depends on the coding system that one is using. Is it the one of 8 bits? Is it of the 24 bits? Is it of the 16 bits, etc., etc.? So that's the first issue. How many bits are coding a pixel? How many bits? And that spreads across all the pixels. So if you decide 8, then all the pixels are coded with 8 bits. If you choose 16, then all your pixels are coded with 16 bits. If you choose 32 to code your pixel, so every pixel has 32 bits. Then now the combinations. So the combinations now, code the different colors. So depending on the coding system for there, you have different colors. So that's how it is going to create different, or it will have your pixels having different colors. So some of your pixels will be red, some will be blue, some will be yellow, depending on its code. What is that is the code, the bit code, the combination of bits. Just like we were talking about, if you have 3 bits, how many combinations, different combinations of codes can you have? Because in that case, like for the 3 bits, all zeros, so you notice that the combination each has 3 bits. So the 000, maybe 101. So all of them each has 3 bits, but they are different combination. Each combination creates or represents a different item. So if it's a color, each will be representing a different color. So the 000 will be one color, 001 will be another color, 101 will be another color, etc. And that is how finally the various colors can be created and displayed. Now, that I have taken a bit long there, trying to capture the question of Ian Kimathi. So, Kimathi, it depends first of all, decide how many bits do you want to use to represent a point. And once you choose that, every point will take the same. So we don't use different bits, the number of bits for different points. No, it's you make a choice, and once you make a choice, that will be for every pixel. So if you decide you are going to use 16 bits, then every pixel is 16 bits, 16 bits, 16 bits. But now the difference, if it is for them to show different colors, now it is the issue of deciding what is the code for red, what is the code for yellow, and it will be 16 bits. What is the code for blue, and it will be 16 bits. What is the code for maybe all these other colors, the gray, etc., etc. So all those. So first of all, how many bits do you want to use to repeat to code a point or a pixel? Then from there, what combination makes a red? How many, that is in terms of bit combinations, the bits combinations. So the bit combinations, then you can have the different colors that your system can create and display. Okay, so Mamboleo is adding some more comment there that black and white are not among us primary colors. Now that's what we are saying. We normally have primary colors, red, blue, and green. Computer-wise, are considered to be primary colors. I think in the paint world, when you talk about paints, paints, we also do mix paints and create other colors. So you can have maybe now this combination, I don't know what it would give, maybe a red paint and a green paint and the blue paint. You mix them up, they will come up with a different color. That is in the paint world. So we already familiar with that concept, and that is a similar thing that is happening there. Of course, the whole process is slightly different. We'll actually be looking at the 2 different ways of creating colors. They are not all the same. The one of the computer is slightly different from the one of the paint, but the concept is very similar, that you can mix certain colors to create another color out of the 2. But of course, there is also the concept of the primary colors. The primary colors, which are normally, I think that is what we learned in the previously about the the primary colors and the secondary colors, I think it was based on paints. But there is also the mixing of light. Remember, light, we say light consists of 7 colors. So when the 7 colors of the rainbow mix perfectly, then they create what we call white light. Or light, actually, we call it just light. Because it's not white. We talk about light. There is a difference between light and white. We need to remember that. But we say when the 7 colors of the rainbow mix perfectly, then they become light. And the light, we even try to do some experiments, some demonstrations, how you can actually see these 7 colors of the rainbow by putting something that actually could do the splitting, to split the colors in light and show the various colors, what we normally say are the colors of the rainbow. So you can also mix light, different colors of light. We actually call them different light colors. Okay, different light colors. We can mix different light colors and get other types of colors. And that is the kind of system that the computer normally uses. But there is also the concept of the paints, where you can actually mix certain colors and end up creating another color altogether. So I hadn't looked at this concept of primary colors and all that. So I don't want to tell you which are the primary colors right now. But this RGB concept that I'm demonstrating here, RGB is actually one of the models that the computer uses to create the other colors by mixing up. So it's for the computer is an issue of mixing light in a color, what we are calling colored light. Is about colored light mixing to create another color. Of course, which is also going to be just a light. It's not a material like the paint. So it's just a color for the sake of color, and not it's not like the case of the paints, where the paint, of course, creates another paint, but Okay, all right. Sorry, students, for that. I forgot to power my computer. Then it went off just suddenly. I'm very, very sorry for that. But we can conclude. We essentially have covered what we wanted to cover for today, as I said. But I was just about to add, and this is just confirming you that you must be aware that we should be doing our cut one a little earlier than we had suggested, because of all the we're trying to handle several things at the same time to save time and also to make sure that your studies are not delayed in any way. And so the cut one will come early, as early as next week. And also earlier on, I had suggested we may do it as a take home, like we normally do when we normally do the face-to-face. But again, cut one and cut two, normally we do it as a sit-in. But I suggested you could have it as a takeaway, because we are not sure whether there are other ways of handling that. And so this time we'll not have it as takeaway, and we'll have it going through the system that the university has come up with. There is a system for that we can use to even do the exams as a part of the online. And so we'll do the cut one also by using the same system. And that will be in the coming week, the day of our class. Then next week, we'll be doing our cut one. And that also, actually, according to the way we had put it in the course outline, this is week 4. So probably that will also be the right time also to send the assignment 1. But of course, the assignment, it will be something that you can do over time. But it will also, of course, it will still be online, but it will not be done in a limited way like the way the cut will be. So that one you can actually do it. Of course, I will give a week for the assignment 1 to be done. But I think I will also have the assignment 1 also ready next week and have it available at the portal for you to do the assignment 1 as well. But remember, the cut 1 therefore will be coming next week and will be done online according to the instructions from the department. All right, so unless there is a specific question or point of clarification that I would like Mwalimu to do, I think in terms of what I had planned for presentation for today, I'm done, but I can get in a